Okay, we are here at 12 noon, and it is another Lunch and Learn from the LiDAR Pros. We're grateful for those of you who are joining us, or those of you who are watching this after the live presentation on our YouTube and Facebook channels. This afternoon, we're going to very rapidly go over LiDAR and photogrammetry, which is best for your particular project and where you should be using one or the other, or at least providing information about one or the other for various applications and workflows. So, what is it that we do with both LiDAR and photogrammetry? Well, regardless of whether we're working with LiDAR or photogrammetry, our initial result or our initial deliverable is going to be a point cloud. And that point cloud can come in either high resolution point clouds or low resolution point clouds, from which we can create meshes, and we can create contours, orthomosaics. We can create digital surface models, digital terrain models, digital elevation models, etc. So before we get diving into how we use these, let's have a real quick look at exactly what each one of them is. So we're going to start off by looking at LiDAR. LiDAR is an acronym. It stands for Light Detection and Ranging. And so essentially LiDAR is sending out a beam pulse that strikes a surface and it bounces back to the sensor. And the amount of time that it takes to bounce that signal back is what determines distance. So there are a variety of different ways that LiDAR works, or rather that LiDAR hits and strikes, and there are different grades of LiDAR, from very low-end LiDAR like we find on an Apple iPhone kind of a scenario, etc. So at the end of the day, let's just let me pull up my screen here so we can start having a look at what I'm talking about. There we go. So on the left here, you see a photogrammetry capture. On the right, you see a LiDAR capture of a deep open pit. You can see they display differently, etc. And again, as we look at some of these different formats, we look at the point cloud where we start, our meshes, contours, orthomosaics, etc. So here we've got an image of a LiDAR scan. Whoops, we jumped forward there. Here we've got an image of a LiDAR scan over a piece of commercial property here. This is a basic LiDAR scan. It's not been colorized. In other words, it's just demonstrating or showing information that was captured by the LiDAR itself. We can colorize this. We can apply photographs over this. We'll come to that in just a moment. So effectively, we're sending a beam from the air down to the ground. It strikes trees, the ground, other kinds of things, and then sends that beam back. And that time measurement, or that reflection, is what gives us our distance. So here's a interesting little graphic, or fun little graphic, that shows us how it works. Basically, there's a laser beam that is projected onto, in the case of mechanical LiDAR, it's projected onto a mirror that rotates 360 degrees at very high speed. And that laser pulse then is returned from anything that it strikes. So you can see here, for example, as it's striking the column that's in this room, it's creating part of a partial draw. Now, as the LiDAR moves around the air and moves through this environment, this is how we get that really nice looking 3D plot that comes out of each one of these different technologies. Now, LiDAR comes in a couple of different types. Comes in a SLAM LiDAR. We can get into a solid state LiDAR. We have mechanical LiDAR, as you're seeing in this particular shot. We'll come back to what each of these are in just a little bit. But photogrammetry works a little differently. Photogrammetry takes a series of pictures. Those pictures overlap each other. So as we're looking at any one image, there are at least 4 images that surround it. So if you can, the easiest way, I suppose, to imagine it is, if you've got a photograph, there's a photograph that overlaps, 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 and overlaps. And that is what delivers us one specific section on the ground, or that blend of mixed photographs that we have there. Let's get back to our screen. And so here you can see a large number of photographs over this park that's about to be redeveloped or renovated. And so these images all overlap, and then they come down to the ground and they create what is called a point cloud. Now, in this particular case, we're looking at a colorized point cloud. So this is a point cloud that has the same type of underlying points as we saw in the LiDAR piece. But in this case, the colors are being achieved by taking pixels from the photographs and applying that to that LiDAR point cloud. This is not applying what we would call a mesh, where the full photograph is applied over top of the point cloud. So we'll come to that in just a moment. Now, in many cases, we can actually do both. So here we're looking at a 535 imager. This comes to us from the folks at GeoQ. And the 535 has got the 535 has got three Sony 20 megapixel imagers built into the bottom of it. So not only are we capturing LiDAR data, but we're able to capture photogrammetric data that can be laid on top of that LiDAR point cloud. Now, the real beauty of this particular type of system is that the photographs and the photogrammetry and the LiDAR are cut, or they're matched to the same angle. So in other words, we don't have data sets that cannot be laid over top of each other without registration. So in other words, what area is captured by LiDAR is the same area that's captured via the photogrammetry. Let's dial a little bit more deeply into a point cloud. So a point cloud is really just a discrete set of XYZ points in space. A LiDAR point cloud is developed out of data very similar to what you would find in an Excel file. So you've got XYZ point data that is very similar to if we had an individual that was walking through a physical area, putting down a GPS device and capturing a point. The difference is that a human being can capture, if they're a very efficient human being, can capture about 600 to 700 points in an hour in a day at very best. A LiDAR platform, on the other hand, will capture 600 to 700 points in under a second. So this LiDAR system can capture more points and more data in a 5-minute flight than a human being would be able to capture in walking over an area over the course of 3 or 4 days. So we capture much more data, much more point information. Another way to think of a point cloud in a 2D space is if you've ever seen how a tattoo is created. A tattoo is just a series of dots that are placed into its medium, a piece of skin or leather, whatever it is that we're marking. And those dots eventually join together to create an image. And that's the idea of a point cloud. So here's an example of a point cloud that is also not colorized. What we're seeing here is a point cloud that has got colors applied based on height. So this particular kind of point cloud is used in identifying encroachment areas. Where are trees encroaching on power lines? This is a very important use of systems because it helps keep our trees out of the power lines, which means when the wind blows, the trees don't knock into the power lines and break the power lines, or the power lines don't short and create fires in the trees. There's a number of different reasons. LiDAR excels in this particular application for a couple of reasons. The first of which is it's very, very fast and can give us precise measurements. And additionally, we can feed this LiDAR data into some different types of AI software that can automatically identify those encroachments and spit out an encroachment report, so we don't have humans that are going through and examining each tree, each limb, each branch, etc. in this process. But at the end of the day, the bigger point right now is that you're seeing a LiDAR point cloud. Now let's look at something that's photogrammetry. So this is a photogrammetric point cloud that has had a mesh of pictures laid over top of it. So this was captured with a photogrammetry drone. It built a point cloud. We then took the images, the photos of that point cloud, and we draped them over top of the point cloud that we saw. There's a couple of things that we can do with this. One of the fastest things that we can do with this, of course, is have a great visualization of everything that's here. We can also measure things in the scene. In this case, we've measured some of the volumetrics. In other words, how big are these stockpiles that we see up here? We might use measurements to verify that our data is in place. So these two formats can work hand in hand together. The biggest difference is time. So to develop a point cloud similar to the one that you see here, we're going to run that flight through. And in this particular case, this is about a 5 to 7 minute flight. The processing of this data to see it in its raw form is going to be between 5 and 10 minutes at most. And then we can start cleaning that point cloud if we need to. If we don't need to clean the point cloud, we can feed this into our AI software that's going to discover or look into our encroachments, and it will deliver that encroachment report in under 5 minutes. So anytime we're dealing with LiDAR, the deliverables are very, very fast, nearly instantaneous. When we're dealing with photogrammetry, we're not dealing with just XYZ points in an Excel file. We're dealing with photographs and pixels. And anytime we're processing pixels, it takes significantly more time. Now, one of the questions that we get asked a lot, especially in the survey and construction side of the industry, is how does the aircraft manage to be precise? Can we be accurate and can we be precise? And the answer is yes, we can. We have a variety of technologies, whether it's an RTK real-time kinematic access to GPS data or a PPK, which is a post-process kinematic format. It allows us to get very precise from the air to the ground, localizing our grids to whatever plane system you might be or coordinate system you might be working with. Now, there are other factors as well. We look at the altitude of our flight. Altitude of our flight has a huge component in our discussion of accuracy and precision. So ideally, we want to fly as low and as slow as we possibly can in most instances. If we're going to be dealing with photogrammetry, and we're dealing with low resolution cameras, we're typically going to fly somewhere right around 100 feet if we're looking at 1 centimeter per pixel. Sometimes we need tighter accuracy and sometimes we need lesser accuracy, depending on what the final deliverable is being used for. If we're simply doing progress reporting on a construction job site, we don't need really tight accuracy, and a centimeter of accuracy is perfectly fine. If we're flying in an area where somebody's going to be looking at boundaries and corners, etc., we're typically going to be flying at about 66 feet with one of these smaller imager systems. Now, the higher our resolution is, the higher we can fly. So as you can see here with a 22 megapixel camera, we're going to get a centimeter per pixel at about 100 feet of altitude. A 40 megapixel camera will give us that same 1 centimeter per pixel at 200 feet. And of course, we can go up to a 60 megapixel camera and we're going to get that same measurement at approximately 290 feet or nearly 300 feet. So the higher the resolution of our camera is, means the higher we can fly. The higher we can fly, the faster our job gets done. Typically with LiDAR, we're going to be flying at 325 feet or lower for our best GSD and our best resolution. We don't measure LiDAR data in terms of centimeters per pixel like we do in the photogrammetry world. We measure points per meter, points per square meter. And so that's how we focus on our resolutions. If we are going to be coupling LiDAR with photogrammetry, we're typically going to be flying below 300 feet. So again, more pixels do equal greater precision. So whether we're dealing with photogrammetry or we're dealing with LiDAR, the lower we can fly in most scenarios, we'll get greater data density or greater pixel density. And this is one of the things that makes a big difference. This is easier to illustrate if we look at something like the stockpiles that we see right here. So we see a stockpile with a small sensor with low GSD. We can see that we don't have a tremendous amount of accuracy in this particular scene. But when we jump that up to a 40 megapixel or a 60 megapixel camera, we get significantly more data into that piece. Now, in our case, we frequently use Pix4D for most of our photogrammatic assemblies. Pix4D is becoming an industry standard, replacing the very deep industry standard of Pix4D Mapper, which is kind of long in the tooth. Pix4D is the new version of Mapper, if you will. It works much faster. It's got reality capture built into it, and we'd be happy to provide a demo for you in Pix4D or do an online training piece with you. But let's keep talking about what else we can do with LiDAR and photogrammetry here, as I'm starting to run really short on time. We can output a digital surface model. That gives us everything that's on the surface, including houses and trees and cars and so on and so forth. We can also output a digital terrain model, which just simply shows us dirt. Well, when we're dealing with photogrammetry, it's very difficult to output a digital terrain model because tree branches and so forth obscure the ground and photographs can't see through those trees. On the other hand, if we're dealing with LiDAR, laser can penetrate through the tree canopy and get right down to the soil underneath, giving us a perfect surface model. Now, again, what we'll do is we'll fly a fur point cloud. Then if we wish, we can throw a mesh on top of that, and that gives us our surface information that's there. We can use LiDAR or photogrammetry to output contours. Again, the conversation is really one of speed and one of precision. If we're dealing with LiDAR, developing 1 foot contours is no challenge whatsoever, and we can output that data in a very, very rapid period of time. Where we're dealing with photogrammetry, we can also output contours. Depending on the camera that's used, resolution may be lesser. We might not be able to get down to 1 foot contours if we're using a low resolution RGB sensor or photogrammetric sensor, but we still can do it. It's the render and output time that's going to cost us a little bit. So then from here, we're going to be able to go into images where we create a mosaic data set. We can use this for basic measurements. We can use this for marketing a property. We can use this for indicating what our takeoffs should be. So for example, if we had a scan of a home like this with a roof, we can output this data into a product such as Roof Scan or other types of software that'll tell us exactly what our bill of materials is going to be, so we understand our takeoffs. How many squares of shingles do we need to buy to cover this house? Or perhaps we might be calculating fertilizer for a yard or for a golf course, etc. All of these things can be achieved from this orthomosaic that you're looking at. So where is photogrammetry ideal? Photogrammetry is ideal where we don't have to penetrate vegetation anytime that we don't need to get a perfect dirt model. They're great for colorized model for marketing and visualizing, and even exports into CAD. We can extract surfaces from photogrammetry and drop straight into Revit or other CAD tool that we might have. If we need high localization, where we get deep precision on the ground, getting down to sub-centimeter levels, we can do this. All of our photogrammetry models out there, even with low resolution cameras, will generally get us into the 1 to 2 centimeters per pixel region. It works great in daylight. Photogrammetry is ideal for daylight flight where we've got plenty of sun and plenty of light. Basically, if your eye can see it, so can a photogrammetric camera. It's easy to process. We can train people to be up, flying, and outputting data in the course of just a single day or usually 2 days for really deep information. And it's quite easy to deliver to non-professionals in virtual design over the cloud, etc. And the cost of photogrammetry is fairly low. To get into a very high-end photogrammetric processing system with software, training, hardware, everything all inclusive is about $10,000. And again, that $10,000 price point gets you a base station, a drone. It gets you your photogrammetric software, gets you training so that you understand how all of these things work. So it's basically a business in a box for less than $10,000. Where photogrammetry kind of struggles is in dark areas where we don't have augmented lighting or where we've got heavy tree foliage that's covering the ground area. There is no fast photogrammetric processing because we have to process every pixel. So basically, for every 1 minute of flight time, you're going to count on approximately 10 minutes of processing time, depending on computer speed. If you've got lots of RAM and a high-speed video card, we can shorten that span, but it's still never going to be as fast as we deal with LiDAR data. So where does LiDAR data excel? When we need flight to finish and we have to have speedy outputs, our engineers need same-day delivery or next-day delivery of data. LiDAR is generally the way to go, especially if we're dealing with very large areas. So when time on target is limited, it might be that we've got a roadway and we can only shut down the roadway for a short period of time to capture this data. That's what we call time on target. How much flight time can we have over that area of interest? It works great in dark environments. In fact, LiDAR is frequently flown after business hours into the nighttime. Why? Because there's fewer people that are on the surface. We're not dealing as much with surface temperatures, and therefore winds are generally a little bit lower, etc. LiDAR doesn't care if there's daylight. The only time we're concerned about daylight is if we have to colorize or create a mesh of that point cloud. And then last but not least, LiDAR is amazing when we have multiple delivery formats and we need to just simply be able to convert formats for various kinds of delivery to make meet our customers' requirements. LiDAR is challenged in areas where we've got reflective surfaces or such as snow or moving water or rain. So the image that you see right here was captured during immediately after a light rainstorm. And everywhere you see black there, that is actually concrete surface, but it's covered in standing water. And so the laser beam reflects off that water and we are unable to get accurate measurements. And we process all of this data inside of a tool called LP360. There's lots of different ways to process, but in-house here we use LP360, and LP360 comes as a component to any of the GeoQ sensors that we sell in the LiDAR world. LP360 is a very common LiDAR post-processing tool. It is rapidly becoming known as the Photoshop for LiDAR sensors, if you will. It is capable of bringing in multiple types of LiDAR processes, LAS files, etc. So whether you're working with systems as diverse as the GeoSun solid state LiDAR, all the way out to the Wingtra fixed wing LiDAR, bringing in any of the GeoQ LiDAR, etc., LP360 is the choice of most professionals when they're working in a professional LiDAR processing environment. It is very, very fast. It's remarkably robust. It's easy to spit out lots and lots of kinds of deliverables. Now, before we wrap up here, let's talk about where LiDAR is very consistently used. So, for example, here we've got a scan of a building that's going to be receiving a new facade. Here we're seeing LiDAR used in an interior setting where the LiDAR data has been used to extract surfaces to create a CAD model of the inside of that very same building. LiDAR is fantastic for as-built. It's great for asset verifications if you're dealing with things like ALTA surveys for land and title surveys. If you're doing volumetric calculations, if you're doing any kind of BIM modeling or building a BIM book, LiDAR excels in all of these different areas. For digital twinning, LiDAR is unbeatable, especially for speed. Other things where LiDAR is really great is anywhere we don't need light. If we got canopy penetration, we need repeatable accuracy, and we need to be efficient in large working areas. So this is a scan of an airport down in Alabama. This is a very fast scan that was achieved during a mobile LiDAR scan, driving around the airport with the LiDAR mounted on a car versus on a drone. One of the benefits of some of the LiDAR systems that are out there is they can be dual purposed. Now, one thing that you may not know about the team here at LiDARPROs, we certainly provide LiDAR services where we fly LiDAR areas, or we fly LiDAR photogrammetry for a variety of construction, engineering, and development companies that are out there. But we also work very closely with the manufacturers to help develop some of this equipment. So this is Brady and Ben, myself, we're down in Alabama at GeoQ, and what you're seeing flown here is the new GeoQ 540. This is an engineering grade LiDAR system. It's mounted on an NDAA compliant MapTech airframe here. You can see it flying in place there. Again, this is an engineering grade LiDAR system. This would get us down to about 15 millimeters of accuracy on the ground. So it's a little better than some of the other systems that are out there that are giving us about a centimeter of accuracy on the ground. By the way, the same sensor can be flown on a variety of different platforms. So that wraps up what I have to share with us today. Unless we've got some questions that are out there, I have not seen any questions come through on my chat. Oh, here's a couple of questions from Facebook. Can you use any type of drone for photogrammetry? As long as the camera system, or I should say the drone system, is capable of automated flight, you'll be suitable for photogrammetry. Basically, what happens is the camera records latitude, longitude, and altitude data in the metadata on the camera. Where this can run into some trouble, folks want to do photogrammetry with some types of drones, such as, say, some of the smaller DJI drones. They're not set up for automation, and so some folks say, well, you can't use that for photogrammetry then. Well, you can. We just have to manually fly grids, which means we're introducing significant amounts of human error factor when we're putting these together. So the short answer to that question of can you use any type of drone or camera for photogrammetry, the answer is yes. The longer answer is how good do you want it to be? Then, do we have any good ground-based solutions for photogrammetry and LiDAR? We absolutely do. We've got static-mounted LiDAR systems, and then for ground-based photogrammetry, things like the Ricoh Theta or Insta360, a lot of these cameras are capable of doing ground-based photogrammetry. Bear in mind, it's going to be significantly slower, but you'll also be building 3D models directly from the ground. As far as ground LiDAR, we can take the very same LiDAR, the systems that we fly in the air, and mount them to vehicles. We also have handheld SLAM LiDAR systems, which at current point are not quite as robust, as accurate as our aerial LiDAR systems are, but they certainly exist, and we're capable of using them out there. So yes, we can operate both terrestrially and from the air. And ultimately, the very best scans you're ever going to see are where we have terrestrial scans, be they photogrammetry or otherwise, combined with aerial scans. And most of our software tools will allow us to register aerial data with data down on the ground. So we can get quite a bit out of both of these systems and combining them together. And I don't see anything else coming through, so we're just going to go ahead and wrap this one up until next week. Please join Ben Goddard next week, where we'll be discussing different types of aerial platforms for carrying different kinds of sensors, or various kinds of sensors. So we'll be talking a lot about MapTech and Wingtra. We'll be talking about Inspired Flight, and we'll be talking about Microdrone. We'll also be discussing DJI and Autel and some of the other platforms that are out there, and where they're appropriate and where they may not necessarily be appropriate or efficient. So until next week, thanks for joining us here at the LiDAR Pros. We'll see you soon. Take care, everyone. Be safe.